This is the first of several screencasts on Chapter 3, Chemical Reactions. A lot of this is going to be a review from first year chemistry, but I do want to hit some highlights and hopefully refresh your memory, as well as cover some philosophy and theology and history in this chapter that is seldom on tests, but is the kind of stuff that you should understand if you're going to go deep into science, particularly chemistry. In this particular introductory page, we have a picture of something called a black smoker. And as we look at the text, you can see we're going to be talking about metal sulfides. Another phrase would be metallic sulfides. You should remember from first year chem that "ide" means elemental sulfur that has donated its electrons to the metals which like to receive electrons. So instead of a sulfate or a sulfite, this is going to be a sulfide. And in any case, we find these at the very bottom of the ocean, particularly the Pacific Ocean along the East Pacific part of the continental waters. And we also can find them associated with volcanoes, like the picture on the right from St. Lucia in the Caribbean. And this black color is because insoluble sulfides, of course the word insoluble means doesn't dissolve in water, often are black, which is kind of interesting because elemental sulfur is yellow. Powdered sulfur is a yellow color, but as soon as you make sulfur compounds that are insoluble, the coloration is black. In any case, thinking about these pictures, there's a lot to learn as we study them, because some of this relates to a very important discovery made way back in 1912, or at least I should call this a hypothesis or a theory, that the surface of the Earth, the crust of the Earth, which is very, very thin compared to the overall radius of the Earth. If you think about a very, very large balloon, you could think that the thickness of the material of the balloon itself is very, very thin, just like the thickness of the crust of the Earth is very, very thin compared to the overall radius or diameter. In any case, also think about a tangerine, and you go to peel the tangerine in order to eat the pieces inside. You could, if you wanted to, sort of put the pieces of the tangerine back together again. Those pieces would be called tectonic plates or pieces of the tectonic plate, and they are constantly moving over time. Sometimes they move on top of each other. Sometimes they push against each other and bulge upward. Sometimes they spread apart and magma from beneath has to come up to replace the gap in between. This all goes to this study of plate tectonics. But this theory was first proposed in 1912 by Alfred Wegener, and he was basically laughed at or mocked at or pretty much dismissed, because that's a pretty wild idea to think that there are crustal plates, much less that they're moving around. We now know that his model and his idea is absolutely correct. Now, going from there, we recognize that when one crustal plate smashes into another, something's got to give. And often one plate will begin to slide over and above and across the other plate, pushing it down towards the center of the Earth. And when that happens, it heats up. And of course, it goes to 300 to 400 degrees Celsius within the Earth's crust. And as you might imagine, since water boils at 100 degrees Celsius, but you're under a tremendous pressure, you're going to get superheated water, where it's still in its liquid state, but it's well above its ordinary boiling point. Not only that, but it's going to be so hot that lots of the material of the crust at that temperature is also going to become kind of liquid. But in any case, this 300 to 400 degrees Celsius superheated water is going to increase the solubility of the minerals. The hotter the water gets, almost all minerals become more soluble. The colder the water gets, almost all minerals become less soluble. So these minerals, when they finally get to a place where it begins to cool, are going to precipitate out. And a lot of those precipitates are metallic sulfides that are black. And you can see them as they are produced in the heat where these crustal plates are subducting, meaning one is going over the top of the other, or subduction would be where one is going underneath another and scraping against it, producing the heat. When it encounters the cooler ocean water above it, it begins to precipitate, and you get all these black minerals. Now, what's also very amazing over here is that there are some very, very unusual animals that are somehow able to survive in this very hot, sulfide-rich environment. They would not be able to live any other place. And you might want to be asked the question, and we should, just how is it possible that these animals can live at this extreme, inhospitable environment? Even more so, where did those animals come from? What process can create or develop or evolve animals that can have whatever specialized structures and systems it takes to survive in these environments that would kill just about anything else? We would call them extremophiles. And we find them in the hot springs of Yellowstone. We find them in places where mining has taken place and you have these toxic metallic environments. We find them deep under the Earth's crust at very, very high pressures, ultrabaric pressures. So we find them in lots of different places in the Earth's crust. And your text blithely says, these animals have developed a way to live. Now think about that. It's not like these animals are sitting around saying, boy, it's getting hot, it's getting toxic, it's getting high pressure. How are we going to survive? I know, let's have a mutation that makes this possible. Mutations aren't going to be able to do that. What we have here are actually animals with extraordinary capabilities to survive these environments that are very, very opposed to ordinary types of life. And this information that they have that makes it possible for them to persist is requires extraordinarily complicated and exotic kinds of programming in their DNA so that they have the facility to do this. These organisms have this from the beginning. They don't go searching around over millions of years trying to come up with an accidental mutation which it can hold on to, hoping that maybe this mutation, that when added to countless other mutations, can create some kind of protein or other devices by which it can survive these inhospitable environments. Obviously, this is going to be the best explanation is there's going to be design at the bottom of all of this. Ingenious design of mechanisms and processes that enables these organisms to survive in these harsh environments where we would not expect to find life. One of my early research experiences at the Idaho National Engineering Lab in eastern Idaho was actually drawing up pristine, or so we thought, water from deep underground in aquifers that supposedly have never been exposed to the light of day or any organisms that could matriculate down deep enough. And lo and behold, we actually found some microorganisms that were already living in that environment that as best as we can tell had never encountered humans, much less any other kind of life. But the point being that sulfides, if you look at their position underneath oxygen on the periodic table, might have some similar chemical reactions, such like oxides would have, that might enable these organisms to be able to metabolize whatever materials might be there in order to as a basis for their food. And this gets into a later study that you might remember from first year chemistry, where elements in a column in the periodic table have similar properties. All right, so here's the chapter outline and the chapter goals. We'll see how it goes, but I hope to do one screencast and then a second screencast and then a third and then a fourth for chapter 4. So here's where we need to pick up some speed or some steam. And you can see that's highlighted here, that every activity of living things depends on carefully regulated chemical reactions. Now here's another word. Regulated implies something from the outside that is governing, controlling, moderating, guiding, making sure that the chemical reactions are not just taking place, but taking place at the right time, taking place in the right place, and taking place to the right extent or degree or amount. That's what carefully regulated really means when you unpack that phrase. And once again, you're far more likely to expect careful regulation to be the result of planning and purpose than to be accidentally cobbled together by accident with random processes over large amount of times by accident and chance. And once again, I think that to think of something as being intelligently designed, we talked about ID, intelligent design, as being a much better inference to explain this careful regulation than an accidental, mindless process that is unguided and does not have any objective in mind. And you're going to hear me talk about that, if you haven't already, a lot. All right, introduction to chemical equations. First of all, we know that the name of the ingredients in a chemical reaction are called reactants. The reactants are what react. No biggie there. And the things that are produced are called the products. No problem there. And I must say, though, every now and then I have a student that mixes up the reactants and the products. And don't be one of those kinds of students that makes that unintentional mistake, hopefully unintentional. Another thing we know is that the reaction must be balanced. That means that at one level, the same atoms that you have in your reactants, you need to have the same atoms, not just in what those atoms are, but in how many of those atoms there are on the other side as products, because atoms are neither created nor destroyed in a chemical reaction. We also can say that since atoms have mass, because of their protons and neutrons, that mass is neither created nor destroyed in a chemical reaction, the law of conservation of mass. And we can even extend that further to talk about the law of conservation of mass energy. Now, these conservation laws also are not something that are necessarily a given that scientists or people thinking about these things have known about for thousands of years. It's only been within the last 2.5 to 3 centuries we've begun to realize this. And that's because we had to get rid of some crazy ideas that people had 500 years ago and earlier in this field called alchemy, where they thought that because the natural world is mysterious and magical, that maybe things just sort of popped into existence for no explained reason or disappeared for no apparent reason. And people sort of expected this to happen because it was a mystical, magical kind of world. And it wasn't until the Reformation, beginning in the 16th century, the 1500s, during the period of history called the Reformation, when, for biblical reasons, for Christian reasons, there was a rejection of magic. There was a rejection of the unknowable, mysterious. There was a rejection of maybe the gods are doing crazy things as gods are wont to do. But there was the expectation that if there is one God, that one God has one set of truths that apply to both the physical universe, we call those the physical laws of the universe, as well as one set of truths or laws in the spiritual world. And we would call those summarized by the Ten Commandments and further by the law that we should love the Lord our God with all our strength, with all our soul, with all our mind, with all our might, and our neighbor as ourself. There, you would have one set of truths if there is only one God. And if this one God is orderly and rational, we expect the universe to be orderly and rational and not magical and mysterious and unknowable. Now, when I'm using the word magical here, I don't mean magical in the sense of wow and awe and wonder. I mean magical in the sense of like a magician is trying to deceive you or trick you. So we expect these equations to be balanced. And over here in purple, I wrote an equation, and you might recognize that going towards the right, we have the equation for photosynthesis. And let's get rid of that P for photosynthesis. And plants take in carbon dioxide and water and produce glucose, which is this sugar right here, and the oxygen that we breathe. Now, what we need to know is we sort of, without thinking, we write this arrow in there. And that arrow is not something that is magical. That arrow is actually representing thousands of chemical reactions. We don't just mix carbon dioxide and water and bingo, we get glucose and oxygen. There are thousands of chemical reactions between the left side and the right side, and every one of those reactions is regulated by an enzyme. So we see that organic chemical reactions like photosynthesis are extraordinarily complicated, and there is no simple evolutionary or step-by-step automatic, inevitable process that's going to turn carbon dioxide and water into food and oxygen. And we can say the same thing for, let's see, and there we go. We can say the same thing for cellular respiration, CR. Cellular respiration is the taking in plants or eating animals that have eaten plants and breathing in oxygen and producing carbon dioxide and water. And again, that arrow in purple is thousands of chemical reactions. In the process right now, as you're listening to this screencast, you've got at least 2,000 chemical reactions going on, and they're regulated by corresponding enzymes. Extraordinarily complicated process. It's not simple to turn glucose and oxygen into carbon dioxide and water. And let me mention parenthetically that carbon dioxide, when you think of photosynthesis, is plant food. And increases in carbon dioxide, as we've seen during the Industrial Revolution in the last several centuries, actually causes plants to grow more rapidly. And that's why often in greenhouses, they pump carbon dioxide into the greenhouses in order to get the plants to grow a little bit faster. Now, also, we should point out that we are often in our writing our chemical reactions, we designate gases with a G, liquids with an L, solids with an S, and then using the Latin word for aqua for water. The substances that are dissolved in water, we use aqueous. And those are usually ions that we write AQ afterwards. Now, coming down here to the last paragraph on this page, we have a reference to 18th century Antoine Lavoisier, who was a Catholic Christian. And he came up with that matter can neither be created nor destroyed in a chemical reaction. Again, a very logical and Christian idea that would be that would confront the prevailing idea that nature is somehow mysterious and magical and does things without any explanation or order behind it. So you can see why we needed a worldview change in order for Robert Boyle, the father of chemistry and a very devout Protestant Christian in the 17th century, to lay the foundation for Antoine Lavoisier in the 18th century and other chemists for the discipline of chemistry to take off. You needed to jettison some of these old-fashioned and untrue ideas from earlier worldviews. And when this reformational Christian worldview began to take hold within Western civilization, then modern science really began to take off, not only in astronomy and then in physics with Isaac Newton, but also in chemistry and then in earth science and also in biology. So let's move on to the next page. Here we can see some of the ways in which we can do chemical reactions, where we try to carefully regulate the masses or quantities of our reactants and carefully regulate and measure the quantity of the products that we produce. I would not recommend you do this at home because nobody should be working with chlorine gas. And here's a biographical description of Lavoisier. They mentioned a few other scientists named Priestley and Scheele. There's a mention here of publishing. A lot of times discoveries are made concurrently in different places, in different parts of, certainly in Western Europe at the time, or sometimes across the ocean between different continents and different countries. But whoever publishes first is the one who gets an awful lot of the credit. In any case, you can read a little bit about this history, and you can see where the word oxygen came from the Greek for to form an acid, because when you mix oxides in water, you often get acids. You can also see the ways in which discoveries are made. For example, measuring the exhalation from a guinea pig, the amount of carbon dioxide produced, and then also measuring the carbon dioxide produced when you just are breathing and from respiration. And you begin to realize that, or when you're burning carbon in oxygen to get your carbon dioxide, you begin to realize that respiration is just a very, very slow form of combustion. But both of them produce as a product, require as a reactant oxygen gas and produce as a product carbon dioxide. Now Lavoisier, because he came from the bourgeoisie, the wealthy upper class, during the French Revolution, he became a persona non grata, somebody who was seen as a cause of the oppression of the proletariat, of the lower class. And during the French Revolution, which began in 1789, there was a violent overthrow of the aristocracy, and many of the leaders and the politicians and the upper class were killed. It's to pardon the joke or the pun here, but Lavoisier was beheaded. You could say his life was cut short. And that's a very unfortunate play on words there. By the way, there was later on you had the Russian Revolution in 1917, again an attempt to violently overthrow the ruling class. Then you had the Chinese Communist Revolution in 1927. And all of these revolutions, rather than trying to change the government and the rule from within, the effort was to overthrow, and resulted in a tremendous amount of death and destruction. And of course, with the Chinese Revolution, with Mao and the Russian Revolution based on Marx with Lenin and Stalin, you could say in the 20th century that between these despots, you had 100 million people or more who were killed as a result of this violent overthrow. The American Revolution in 1776 was very, very, very different from that for a lot of different reasons. And I say this because tomorrow, as I am making this screencast, is actually July 4th. So you can read about the very big difference the American Revolution was compared to the French, Russian, and Chinese. But also, as I'm recording this, there is an increasing effort even within this country to not just work hard to change the existing laws and the way in which government is done and imposed. In other words, the efforts to make us live up to the Constitution. There are efforts strongly now within our own country, as well as in Europe, like Great Britain, to overthrow the existing institutions and the existing government. And that is very scary. And I pray that we are able to withstand that and not give in to an overthrow of the Constitution and our institutions, but instead to reform them and live up to the Constitution and the Declaration of Independence, where we say that all men are created equal and endowed by their Creator with certain inalienable rights, among which are life, liberty, and the pursuit of happiness. That idea of being created equal and endowed by the Creator comes right out of Genesis 1, 26, 27, and 28, that every human being is made in the image of God. Enough of politics and chemistry for the time being. Here's something you might remember that you learned way back in the fall of your first year chemistry class called stoichiometry. Because of the law of conservation of atoms and the conservation of mass, stoichiometry is this branch of chemistry which enables us to balance these equations. And the word stoichiometry, stoichion is a Greek word that meant element, and metry comes from the Greek word metron, which means to measure. And so in a sense, stoichiometry is the measuring of the elements or the particles of these elements, which we now call atoms, and we expect them to balance up. And so we use subscripts in the formulas, or formulae, Latin plural, and we use coefficients in front of these formulae when we balance our equations. Now, in balancing the equations, hopefully you remember that there are various patterns of reactions that you have to memorize in order to be able to more accurately predict your products. Some of these patterns are going to be talked about now in this chapter. For example, we can have metallic oxides and we can have non-metallic oxides. And metallic oxides are going to be formed when you combine metals and oxygen, for example. And non-metallic oxides would be when you take a non-metal, and you should know where in the periodic table you find your metals on the left side and in the middle, and your non-metals towards the right, but not all the way at the right where the inert gases are. But we take our non-metals and combine with oxygen, and what we get are oxides. So this would be a metallic oxide, a non-metallic oxide, another non-metallic oxide. You should recognize that pattern. Also, now that you're in AP chemistry, you should also be able to do it in reverse. The AP exam often has you balancing equations, but they will give you the reverse of one of the patterns that you've memorized. So that you ought to remember that if you're given a metallic oxide, it decomposes into an oxide and a pure metal sometimes. And a non-metallic oxide can decompose into oxygen and the non-metal. Another pattern of a reaction that you should know is combustion. Combustion, and of course remember respiration is a slow combustion. Oxidation is a slow combustion. And combustion basically means we're combining it with oxygen, and the products of combustion are always going to be carbon dioxide and water. So we take our hydrocarbon, and there are other compounds besides hydrocarbons, particular compounds that look like this, that also, when you combust them in oxygen, produce carbon dioxide and water. So when you get a combustion reaction, you should automatically remember, oh yeah, I need to put plus oxygen as one of the reactants. And the products will be carbon dioxide and water. And you can tell by these coefficients that a lot of times you're going to get some rather big numbers, like 25 and 16 and 18. And I would always balance your oxygen last when you are balancing combustion reactions. That'll make it a little bit easier. And so now your text is going to give you an example of how you go about doing this. You can read these bullet points. But remember that you must always make sure your formulas of every reactant and then every product is correct. The formula must be correct regardless of what the formulas of the reactants are. The formulas of the products have to stand alone as being correct. Don't let what the reactants are influence you into thinking what the products might be in terms of their formulas. Then once we have the formulas correct, then and only then can we begin to put coefficients, which we call them stoichiometric coefficients, to balance the equation. So first we make sure the subscripts are true and accurately reflect what the true identity of the substance is, and then we use our coefficients. And then once we have the correct reactants and products, like we do here, with a combustion reaction, it's easiest to begin with balancing the carbon. And then once you balance the carbon, balance the hydrogens. And then once you balance the hydrogens, balance the oxygens. And sometimes you might even get a fraction when you balance your oxygens. For example, if we were to come back up to the formula, I know what I'm looking for here. It is, hope you're not getting dizzy. There it is. When you first balance this, you might have gotten a 1, and then a 25 divided by 2, and then an 8, and then a 9 when you balance this reaction. And you can leave it like that, which is actually a good thing to do when you're trying to calculate the energy of the reaction, which is a later chapter, or just multiply all your coefficients by 2. And either one would be correct. And here you have an example, which I'm not going to do, of balancing a chemical reaction. Always make sure you verify your result. Check your answer. All right, the last section in our first screencast, it says here that these chemical reactions, the ones we often have been looking at, proceed in one direction. And so we draw the arrow going to the right, going from reactants on the left to products on the right. Well, actually, the majority of chemical reactions don't march from the left all the way to the right. But actually, the majority of reactions reach an equilibrium somewhere in the middle. Those chemical reactions are reversible. Remember, if a reaction goes all the way to the right, it's because one of your products is a gas, is a liquid, like water, which is the most common, or is a solid, which we call a precipitate. Because gases leave the reaction environment, solids go to the bottom, they precipitate out, and molecules like water or a strong or a weak acid or a weak base have such a strong bond. In the case of water, this bond right here, the bond between the hydrogen and hydroxide, is so strong that the energy of most reactions can't break it apart so that the reaction can reverse itself and go to the left. But most chemical reactions, we see this all the time organically, are reversible. So for example, this reaction right here, we have calcium bicarbonate or calcium hydrogen carbonate. Either name is correct. This is a soluble ion. So if we're writing the net ionic reaction, soluble ions, we split up into its ions, one calcium ion and two bicarbonate ions. Calcium carbonate is not soluble. It's a solid. You should recognize that as being marble or limestone or chalk, depending upon how it was formed in the Earth's crust. And then in this double displacement reaction, you produce carbonic acid, which immediately decomposes into carbon dioxide and water. So you can see that this reaction is naturally going to go to the right because this gas is going to bubble away and water has the strong bond that's hard to yank apart. But in a closed environment, so that the carbon dioxide can't escape, but maybe under pressure remains dissolved in water, and with the right energy, you can push this reaction to the left and make it a reversible reaction. Another very famous reaction is this one right here. Ammonia decomposes in the right conditions to nitrogen gas and hydrogen gas. And this might be one way someday to make hydrogen gas if we're trying to combine hydrogen and oxygen to make water in an exothermic reaction. But more importantly, and I want to erase the circle here, because I think more importantly is this reaction right here. This reaction is the reaction that feeds the world. This reaction takes nitrogen gas, and remember, our atmosphere is about 79% nitrogen gas. And nitrogen, you'll recall, has this triple bond, as well as each nitrogen with a lone pair of electrons. So this triple bond is very, very, very difficult to break. It takes a lot of energy to break a triple bond. And in the ambient conditions of our atmosphere, nitrogen, which is N2, Brinkelhoff, N2, doesn't break down, which is a good thing. It makes our atmosphere extraordinarily stable, and it better be because we have so much oxygen gas in it. Almost all the rest of our atmosphere is oxygen gas. And if we didn't have stable nitrogen, that means every time you lit a match or there was a spark or a lightning strike, our whole atmosphere would blow up. And of course, you hate it when that happens. But that doesn't happen because of stable nitrogen. So that means that if we try to combine nitrogen gas with hydrogen gas, nothing really happens unless we have very carefully controlled, regulated conditions of the right pressure, the right temperature, and the right engineering that we can siphon off ammonia as it's produced. We can continually feed in nitrogen and hydrogen gas, and you might recognize the idea of Le Chatelier's principle here, driving the reaction to go to the right. You might also recognize that if we have one molecule of this gas and 3 molecules of this gas, 4 molecules of gas on the left, only 2 molecules of gas on the right. If we have very, very high pressure, it drives the reaction to the right. Don't worry, we'll review Le Chatelier's principle in a later screencast. So you need all of this in place to produce ammonia, And ammonia is an essential ingredient for fertilizer. In fact, ammonia itself is fertilizer. And we should be very, very grateful that this thing does not happen naturally. If this reaction went to the right, let's go with blue. If this reaction naturally went to the right, and of course it doesn't, that means all the nitrogen in our atmosphere would continually be producing ammonia, and ammonia stinks. And so our whole atmosphere would smell like we were in a small room with a whole bunch of wet, dirty diapers. And of course, you do not like that either. You hate it if that were to happen. Now, coming over here, if we were to graph this kind of reaction, you can see in this graph that if we were to take a quantity of pre-existing nitrogen and nitrogen right here, and a quantity of hydrogen gas, notice we need a 3-to-1 ratio. If we were to divide this y-axis up into 3 parts, 2, you can see we got 1 part here, but 1, 2, 3 parts of hydrogen. If we have 3 times as much hydrogen as nitrogen, and we don't have any ammonia to begin with, that's down at 0. And then we make this reaction go to the right with our special engineering, with our high pressure, and so forth. Now we can gradually produce more and more and more nitrogen as we use up hydrogen 3 times the rate that we're using up nitrogen. And pretty soon we flatline. And where we flatline, if this graph on the x-axis is time, this is the moment where we reach equilibrium. This is the moment at which the reaction also becomes reversible. And we have reached chemical equilibrium. And this chemical equilibrium is dynamic. It doesn't mean the reaction is stopped. The reaction stops. What it means is the rate at which nitrogen and hydrogen are producing ammonia is the same as the rate in which ammonia is decomposing back down to nitrogen and hydrogen. And you can see why in the engineering of making ammonia, and we make millions of tons of this a year around the world, if we continually siphon off the ammonia and remove it, the reaction can keep going to the right to replace it. So under specialized conditions, we can make this product favored. But ordinarily, it is not. It stays to the left. It's reactant favored. And you'll remember from first year chemistry, and this is something we'll spend the majority of second semester on, which is equilibrium reactions, we can come up with equilibrium expressions. And these equilibrium expressions for reactions that are at equilibrium, when they're very much greater than 1, this is the reaction that goes to the right and is product favored. When the reaction is less than 1, this is the reaction that is reactant favored. Because remember, my equilibrium constant equals the concentration of my products over the concentration of my reactants. And so when this fraction is greater than 1, it means the numerator is bigger than the denominator. And when it's less than 1, the denominator, where the reactants are, is bigger than the numerator. And we're going to stop here, and we'll pick up with the next screencast the next time you watch it.